Okay, we're going to prove this expression here. It's dn dxn of 1 over x. So in other words, the nth derivative of 1 over x. And we want to show that that's equal to negative 1 to the power of n times n factorial over x to the n plus 1. And this is for any integer value n greater than or equal to 1. Okay, so we're going to use proof by induction. So we'll go through our step-by-step process. You know, it's a bit of an unusual looking one, but we still just keep to the process, which first of all is checking for n is equal to 1. So for n equals 1, really what we've got is d dx of 1 over x. So if you like, d to the power of 1 dx1, or just d dx, or the first derivative of 1 over x. So doing that, if we like, we could say that's equal to d dx of x to the negative 1, and then differentiating we get negative 1 x to the negative 2, which is equal to negative 1 over x squared. Now we want to make sure that this expression is true. In other words, it's equal to this right hand side here. So let's just rearrange this a little bit. We can write this negative 1 as negative 1 to the power of 1. In other words, n is equal to 1 here. And if we like, we can say times by 1 factorial. So for n is equal to 1 over x to the, it's n plus 1. So because n is equal to 1, we could call that 1 plus 1. So we can see that d dx of 1 over x, it does hold. We do get negative 1 to the power of 1 times 1 factorial over x to the 1 plus 1. So we can say, which implies true for n equals 1. Okay, that's our first step. Our next step is where we assume that this statement is true for n is equal to k. So next step, assume true for n equals k. In other words, we say that the kth derivative of 1 over x is equal to negative 1. Oops, let's move that up a little bit. Okay, so we're going to say the kth derivative of 1 over x is going to be equal to negative 1 to the k times k factorial over x to the k plus 1. And we're just assuming that this is true. Then what we want to do is show that it's true for n is equal to k plus 1, given that our assumption is true, given true for n equals k. Okay, in other words, what we want to show is that the k plus 1th derivative, if you like, of 1 over x, this is what we want to show, is going to be equal to negative 1 to the k plus 1 times k plus 1 factorial over x to the power of k plus 1 plus 1. So that'll be, in other words, k plus 2. So this is what we want to show. So I might even put here, i.e. show. So we want to show this statement here. If we can show that's true, oops, just forgot the plus 1 there. If we can show that's true, then our proof is effectively done. Okay, so how do we go about doing that? Let's go to the left-hand side here. Now the left-hand side, we can really think of that as being the derivative of dk, dx, dk of 1 over x. So the k plus 1th derivative is really just the derivative again of what we've already got, dk, dx, k of 1 over x. Okay. Now we also know that from our assumption up here, from this part here, which we've assumed is true, is equal to this part in here. So we can now go and substitute that in, because that's the part that's been assumed. So we can now say that that's equal to d dx of negative 1 to the k times k factorial over x k plus 1. And I'll just put a little note in there since n equals k is assumed true. Just to show what we're doing there. Okay, so from there what we want to do is we want to try and get this whole thing, the derivative of this expression, so that it's equal to the right hand side over here. That's what we're aiming to do. Okay, so let's have a go at that. We can simply go ahead and differentiate this expression then, remembering that what we're differentiating with respect to is x, so really just differentiating this x to the power of k plus 1. So just to clarify things, I might even just rearrange that a bit. So we've got negative 1 to the k times k factorial. I'm going to bring this x to the top line, and in doing so the power becomes a negative. There we go, power of negative k plus 1. That allows us to differentiate this polynomial here quite easily. And we'll get differentiating, so we now drop out this derivative. We get the power here, which is, bring that out the front, so we get negative k plus 1. And then I've got my negative 1 to the k is still there, that's really just a number, times k factorial, which is really just a number. And then our power reduces by 1. So we've got negative, let's call that negative k, take 1, and we take another 1 off that. There we go. Okay, so we're still not quite there. We want to get this expression sort of looking like this one up here. So there's a little bit of work to go, so we're not too far off. So let's have a look at that. Just move it up a little bit. Okay, so at this point here, what I might do is I might bring this x back to the bottom line, because we do want it on the bottom line. So we'll say it's equal to negative k plus 1 times negative 1 to the power of k times k factorial all over. Okay, so this here, if you like, you could think of that as the negative outside of k plus 2. So it comes down to the bottom line here as x to the power of k plus 2. So just sort of thinking of that one there, that's the same as x to the negative k plus 2. Okay, so I've just brought that to the bottom line over here as a positive power. From there we just want to have a look at our negative 1 here, I guess. We can write that the negative as negative 1. We've got negative 1 times negative 1 to the power of k. And then we've got k plus 1 times k factorial all over x to the power of k plus 2. So we're almost there. Finally here we've got negative 1 times negative 1 to the k plus 1. You can think of that as a power of 1 there, so we just add those indices, same base, we get negative 1 to the power of k plus 1. And here we've got k plus 1 times k factorial, so really that's just the same as k plus 1 factorial. Remembering k factorial itself is just k times k take 1 times k take 2 dot 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 all the way down to 3 times 2 times 1. So we just add an extra k plus 1, that's really just k plus 1 factorial all over x to the k plus 2. And if we go right back up here to our right hand side here, we can see we've got to our right hand side. So there it is there, so that's equal to our right hand side. Okay, so which implies if true for n equals k, then true for n equals k plus 1. And we already know that it's true for n equals 1, which implies true for n equals 2, which implies true for n equals 3, dot 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 dot. Hence, let's just move that up a bit, hence proved by induction. have it.